I'll just get started with this. So we just talk mostly about the IRRI's program, as I mentioned earlier. Yeah, and then I've divided my talk into two different sections. In section one, I'll just give very brief background and something about key concepts and when we can start implementing GS in a breeding program. I think it's still relevant to touch bases on that. Of course, there's been a very detailed discussions from Eduardo for the past couple of days. And also from Joseph. So we do know these topics already, but it's still good to have a bit touch bases on them. And section two is what primarily I'll be focusing today is how we are set up to actually implement genomic selection breeding program. So a little bit of background, like why do we even need to modernize the breeding program and what is the requirement? So this is a paper that we are working on in the group where we are all close. It's almost submitted now. Is talking about the historical rate of genetic gain in IRRI since 1960. So you can clearly see on the x-axis is the year and the y-axis is the breeding value for all the individuals. And the trend is not linear. So it goes up during the initial phase of green revolution, it goes down and goes up. And then right now we are in a state where there's a plateau being noticed. So this is a clear indication that we are not making a significant progress and that requires intervention. And how we do that is mainly through modernization efforts in the breeding program. And directly, we are trying to manipulate the Breeders equation and try to increase the rate of genetic gain. So this is the rationale, like why there's a necessity of changing what we're doing in the past and probably address things more effectively. So I would like to also touch base on some of the key concepts. So two things are really important here. One is the recurrent selection breeding strategy. Because whenever we talk about genomic selection, I think it's talking about the population improvement, right? So we need to first of all establish a base population, and that base population is once it's closed, then we are trying to select individuals up within the population and recombine, and then allow that recombination, and then set up the next population. So we do not want to introduce new things every single time from a diverse source or from an older breeding material, so that we make continuous progress in every single cycle. So that's a very a clear and most important step that needs to be done before we even start thinking of implementing genomic selection. So this needs to be one of the strongest and the important point that has to be followed. And the second one is a good understanding of Breeders' equation and see how the components can be manipulated and how we are getting the best gain or bang for the buck, I would say, is how we manipulate each of the components. So how we manipulate selection intensity, how we are manipulating this accuracy, and the genetic variance to an extent, and primarily the genetic, the length of the cycle. So these two concepts is something really important for any breeding program, I would say, in order to even start thinking of implementing genomic selection or any other modernization tool. So that's why I'm making this as like a highlight and just say, okay, before we even talk about GS, I think these two concepts are really important. And just a single slider. So I know this has been covered already. So I just thought of, okay, what is genomic selection? Is just making a decision based on a prediction, which is already done by using genome-wide markers. In some cases, we can also do with pedigree data, but it's effective using genome-wide markers because you can do within family selection too. So this is not a new concept. It has been well established over 2 decades and has been proven to be working in multiple animal species and crops, as discussed in the last few days. So there is no surprise like, okay, will this work? There's been a question being asked to us regularly in multiple forums. So I thought it's an important thing to reiterate once again, is this is not a new concept, and this is definitely a working principle. And how we implement them is the best question to ask, and it requires multiple steps to follow. And also some of the questions that come to us also repeatedly is like, okay, there are multiple ways people try to like compare with genomic selection. So I personally like this diagram from Rex Bernardo's, one of the older articles. It clearly shows like it depends on what is your objective and what is your trait and what is your population. And then you can clearly map what you're trying to achieve, right? So every single technique here is a valid approach. Depends on what you really want to achieve. So for example, if you want to identify QTLs, QTL mapping, association mapping, and then identifying candidate genes, and all these are important and relevant in certain cases where the traits is controlled by few loci, and you're in the discovery phase predominantly. But when you're talking about having more loci, honestly speaking, especially traits like eel, and now we are moving into more of an elite by elite process, and then you're talking about selecting individuals either for parents or for advancing lines, then genome-wide selection is one of the strongest and an important contender to be used to achieve those processes. So this is a good snapshot to show the different array of techniques that are available in breeding programs and how we can place our objectives and how we place our techniques to achieve results. So in that case, as a breeder, we would like to select lines repeatedly, and in a population improvement program where we are trying to use high breeding value individuals, then genome-wide selection is one of the key and working strategies to select for quantitative traits. Okay, so now I think getting on the crux, like when you can start using GS. So I'm not going to many of the other questions like why, where, and when, because it's been covered already. So, but this is an important thing to discuss. Like we need to know or have a checklist in a program, like when can you exactly start? So I have divided into 5 major topics. Of course, they all have individual subtopics within each of them. So I'm sure there'll be more, but at least as a major points, we first have to define an elite individuals or establish a base population. As I mentioned before, in the recurrent selection scheme, we need to have a base population defined. And then we have to probably start doing recurrent selection. We have to make crosses within this population and not go into diverse individuals at some point. And then we also have to have some kind of a rapid generation advanced methods, not do any kind of predicate selection. We need to have a single seed descent. You can do either in a greenhouse or a field, but some way you need to reduce the cycle length, because GS, of course, helps us to increase rate of genetic gain, but we also have to have other generation reducing techniques in order to have an efficient way of increasing your rate of genetic gain. And then this question also been repeatedly asked in the chats and also in the other sessions, like you need to have molecular markers available, and not just any molecular marker, probably most relevant to your crop. And in case of rice, it's also subpopulation specific oftentimes. So if you're working with mostly indica, then you would probably have to have a particular SNP panel. And then this has been covered very well with Eng and then Rajaguru's presentation yesterday, where they've been talking about multiple crops, how they have a genotyping system and platform. So this is an important tool to have before we talk about implementing GS. And then it's not just that it's available, you also need to have it to be routinely done. You need to have genotyping facilities, and then also budget for that, and also the analysis capacity for that. So these 5 things I feel is critical and really important whenever we think of implementing GS in a breeding program, in addition to the other components of breeding program, which I'll explain in a bit. But overall, I'm just trying to distill into the key points. So now I think I'll go into one of my other favorite slides too, in terms of order of importance. It's not very different from what I've been talking before, but in a more like a descriptive manner, like when and is genomic selection is really important, and at where it's actually placed in the pyramid of importance, right? So this is also from Jessica's a paper like a few years back, and which actually maps it really well, like how we are building up the breeding program from the base. And once all the pieces of the pyramid is built very well, then we can start harnessing the effect of genomic selection in a really, really stronger fashion. So let me start briefly from here. And this is also mapped to how IRRI is set up to. So this is a figure that will translate into a practical implication of what IRRI has done. So at the base of the pyramid, first of all, you need to also know what traits you're targeting and which TPE you're targeting to. So this is an important thing, has to be defined initially before we even think of, okay, can we start implementing GS? Now, you need to know what trait you're focusing. Is it a quantitative trait? And where are you targeting to? So how many locations you have and how are these locations distributed? So those kind of things has to be done. This is important in any breeding program. It's more relevant when you're talking about using advanced techniques. And then it is always important to have digitization and also usage of databases, mainly because you will now face influx of data coming into you constantly every single year. So it is really important for us to have some sort of database where you can safely store and reproducible and consistent data structures will come into place. So right now IRRI is using B4R, and future it will be transferred to EBS. It's been using since 2015. So it's also in place. So a meticulous data management, both for phenotype and genotype, is really important in this case. Next is effective operations. This also translates into multiple things. Like you need to make your process very rigidly, and probably genotyping has to be also set up, and line fixation through RGA, seed processing, shipments, and all this will be into effect, because as you've seen from the genetic gain equation, the denominator is the length of the breeding cycle, right? So all these operations will indirectly affect them, although they're not technically complex, but it's still a relevant thing which you need to have it in a breeding program to practically do it faster. So this is an important thing to be set up in place in order to achieve the benefits from genomic selection. And then the next level of the pyramid is effective phenotyping and good trial data. This is one of the most important aspects, I would say, because it feeds the models. And Eduardo rightly mentioned, there are myriads of models and thousands of models you can probably use. But if you have a good trial data, then most of the models produce very similar results. So I don't think we would need to spend a lot of time on which model to use once you have a really good data coming into the system. So effective phenotyping and having good trial data is one of the most important steps in any breeding program, and especially in GS systems. And then you would also have to modify or translate start using mixed models and calculate blubs is also an important change. So previously we can calculate LS means or blues in the case, but it's also effective to start using blub models or mixed models in order to calculate the average of individuals in any given region or multiple regions together. Depends on your analysis. So these 5 blocks would form the very base of the pyramid, and beyond that is what your breeding methods research will come into play. So what type of design or what type of model you're trying to use. So in this case, as I mentioned, so we are trying to use recurrent selection. So it's a population improvement program. So after we build all these things, this is also important that we can, depending on the program. So we are currently following recurrent selection in IRRI, and then I would say most of the programs will do that. So having done all this, then the top of the pyramid is where we are now using genomic selection, right? So when we have all the bases built, then we have effective data coming into system. You're doing effective phenotyping. Then you use those routinely every single year to start predicting the individuals. So, and then also overlay that with high throughput phenotyping, and then using the data. There are so many things you can actually overlay, but all this benefit can only be harnessed when you have your bases built. So it's more like a change or a community of practice, or you're changing your entire system before you start implementing GS. So it's not a silver bullet that solves most of the problem, but it's an effective tool overlaid on the existing changes. So with that, I think I just directly jump into how IRRI is doing, so without taking much time. So section 2, I'll mostly focus on how it's implemented in IRRI. And as been discussed before, the genomic selection is a simple flowchart as shown here. It's a straightforward concept. It's a working concept, but oftentimes it becomes very complex because different breeding programs are in different stages and the goals, strategies are varying. So it becomes really hard to have one single SOP for any breeding program to achieve or implement genomic selection. So in the cartoon figure, like from Hefner et al. In 2009, you can clearly see you need a training population, a set of individuals where you phenotype them, you measure them, and also you genotype them. You train a model, it depends on whatever model you use, and then you use the model to predict a set of untested individuals, and then you calculate a breeding value and make selections. It's as simple as that. But how we integrate into an existing program is what the real question is. So I just wanted to show this mainly because it is a simpler workflow, but when it goes into a breeding program, it becomes slightly more trickier. And it also is depending on the program too. So it depends on the crop. Sometimes, mostly the system itself is crop agnostic, so you can probably extrapolate to any crop. But there are certain specifications, specific breeding program you might need to fit into existing structure. So this pipeline is also a cartoonic figure of an operating a schema, what IRRI is doing. And I purposely call it as phase 1, is because in phase 1, we are using genomic selection mainly to increase selection intensity. We are still not yet using it to reduce cycle time. So it's just the starting of this, and we are getting geared to do that in probably next year. But as of now, we are using it to increase selection intensity. So I'll just walk through this pipeline slowly, and feel free to stop me or ask any questions if you have any. But overall, the breeding strategy hasn't changed. I mean, it's the same concept. You make crosses, you fix the line, you test them, you select them, and you release them. So those things hasn't changed. So in this scheme, I show here like a minimal breedable unit, like where we have 30 to 40 crosses picked, and each of the crosses has population is of 240 individuals. And these crosses the parents are all elite by elite individuals. So once the base population is set up, then you are now picking parents from those base population, and each of them has a population is of 240. And then all of these individuals are being pushed through RGA, where we get almost 3.5 to 4 generations a year in the greenhouse setting in IRRI headquarters. And then once the lines are fixed, then we do grow a hedgerow trial. We call them as LST or line stage trial, where we deploy markers selection for picking mainly for qualitative traits or disease resistance traits, and then reduce the size of the families to 40 or 30 individuals for each. So, and once that is done, we don't do any phenotypic selection until then. And then we have this OYT, which we call the stage 1 cohort. All the lines of the OYT is grown in the headquarters, but whereas a portion of this is sent to all the regions in the target countries or target population of environments. And purposefully, I named this both as stage 1 because these are synonymous. So this is where the genomic prediction also happens. So this entire OYT has 1,200 individuals, for example, and out of which we can only test 200 to 300, and that forms as the training set for this OYT. So this both are stage 1 trials, whereas this one is a small cohort where it's both phenotype and also genotype, and then you use the information to predict the rest of the OYT. So this is where we use genomic prediction effectively, because in this case, all the 1,200 lines are having genotypic data. We do marker profiling using 1K RICA, and then we have genotypic data, but we don't have data for all of them in all locations. Whereas for these 200 lines, we have data from all the locations, and we use them to predict them. And based on these predictions, we have now GBVs for all the lines, and that GBV is now used to do parental selection and form the crossing block for the next cycle, and also use the values to advance lines to the stage 2. So instead of picking the top 50 or the best 50 lines from this the training set, we are now picking the best 50 from the 1,200 lines. And that is how we achieve the intensity, the increased selection intensity, because you're not picking 50 lines from 200, you're picking 50 from 1,200. So this will directly increase the heterogeneity again, because the selection intensity in the numerator. So, and that's how it's been set up. So this blue shaded area is what it depicts what happens in the partner field or what happens in the child locations directly, right? So anything beyond this OYT, everything happens in the region. So the data that comes to me when I do the analysis, it's all coming from the locations directly. So the predictions I do is based on the data I get from the regions itself. This is a significant change from what IRRI was doing 3 or 4 years before, because initially all the steps up until here probably was done in IRRI headquarters or the backyard, where we do the OYT. There were also PYTs and AYTs. All the advanced yield trials were done in Philippines, and then we just send like a set of selected individuals to different regions and hope that would perform very, very good. But whereas now we are now relying on the region data directly to start doing predictions. So this is more relevant because the G by E plays a significant role, especially for traits like yield, and we are now exploiting G by E to have region-based predictions. And this, when I say regions, this can be regions in the initial phases, but now we are also having target concepts based on market segmentation research. So this pipeline could target a specific group of regions where they have similar product concepts. They have similar requirements, similar traits of interest, so that the crossing block can be focused on addressing those traits and those requirements for this. And then once the selection is done, then once one more year, it's been tested in the regions itself again. And then those data is now used to nominate for variety release system. So that is beyond the scope of the breeding program for the IRRI or any NAS partner, because it's all controlled by the governmental rules for any country. So up until here is where the breeding program is actually active, and beyond that, it's been tested for any country. So IRRI is trying to breed for multiple countries in the globe. So this changes a lot based on where you're breeding for. But overall scheme, this is what is going on here. And as of now, we have a cycle time length of about 4 years. And in the coming years, we are trying to reduce it to 3 or even 2 years by having multi-year data and then start doing predictions without waiting for being tested. So that's something that we are already working on actively, and which if you have time, I can show that also. But right now, I'm not going showing the sake of time. But as of now, it's 4-year cycle, because that's what the recycling of the parent happens. And then the product development also happens in parallel. So this is the gist of what how IRRI is set up to deploy genomic selection and then use the prediction-based values to both select parents and also advance lines. In that case, I'm now giving little more details, like how exactly IRRI is set up to implement GS. So there are multiple factors I've been discussing before, and also some of the points have been previously discussed in more detail in the previous presentations. But the first one is we have to close the breeding program. So this is done already. So there was a research on the PhD Scholar like 3 years back, Juma et al., like where we have done a multi-year analysis and then identify a set of high breeding value individuals for yield and also having high reliability and formed as a base population. And right now, it was done 3 years back. So right now we have flushed out the previous programs, advanced yield trial lines. And now we are in a stage where we are using crosses based on that base population only. So that is an important and most as a starting point that was established in IRRI before. And we'll be reading the paper will be out very soon, and probably you can get more details on that or reach out to me if you have any questions. But that was one of the initial steps done in IRRI in the start of the GS program, the GS implementation. And then there was also a clear definition of the genotyping markers, what we need to use. So it was specifically designed based on the subpopulation, indica subpopulation that we have. And it currently consists of 1,000 markers that is distributed across all 12 chromosomes. And it's been routinely used for genotyping all the OIT or stage 1 trials in every single year. And it's done through multiple platforms, Agriplex and DART, and Eng and Rajguru has already talked a lot about it, but that's what IRRI currently has. And then we also have partner engagement being established. So where we get the trials grown. So we don't grow anything here to do the prediction. So we rely on the partners for all the trials in the given TPE. So let it be Bangladesh or India or Eastern Southern Africa. So all of the trials coming from the partners directly, and that's what feeds all the models in reality. And then for cycle time reduction, in addition to GS, we have RGA in place where we follow a greenhouse-based RGA. And this system was already in place even before 2017 by the previous Bert Collard. And so luckily we have the system, so we do not have to wait for a couple of years to fix a line. And that's very handy, which in combination with GS will be very effective. And the other thing that has been developed is digitized data collection. We try to use handheld devices to collect data and to record data into B4R. That's the breeding for results platform. And right now, we also use Android devices using Fieldbook applications. So some sort of digitized data collection to avoid any errors and all those things. So this is an important tool to save time and save error in terms of data quality. And data management is all done in the database. And I've already mentioned about it briefly. And also we have developed semi-automated and data analysis pipeline, both for analysis and reporting using R and ASML-R. This is an important tool until the EBS is fully functional so that we can have the analysis done very fast and we can make decisions very quick. So when we get trial data somewhere in January or February, then we need to make all the decisions done and then have it ready by March or April for the advancements to happen. Because of pandemic, there's been some delay, but usually that's the routine. So these are some of the components that needs to be in place that will help us to do GS routinely, right? So if one of them is not in place, then the wheel wouldn't actually run. Like otherwise, it'll take more time. It can either give you a bottleneck, or it might be giving you a delay in processing your results. So I would say all of these points together, a culmination of effort would be the key for implementing GS. So this is also mapping very clearly with the pyramid I was showing before. So where we have all these points addressed in some level, and then we have built the system to deliver in terms of getting the predictions and using the predictions effectively to make the decisions. So in terms of, I'm just diving directly into the GS analysis framework directly, right? How do we do the analysis, right? So for example, I've shown in the picture the OIT or the stage 1 trial where all the lines are being genotyped, right? So that is done during a wet season here, and using the information, we construct the G matrix, and then that matrix actually used to pick the training set. And that training set is now sent for multi-environment evaluation. And then we do a 2-step model as of now, because in the past we had diverse experimental designs and we wanted to accommodate those things. So we were doing a trial by trial analysis initially and get some sort of means, either blubs, sometimes blues, to get a value of the individuals. And that output actually feeds for the genomic prediction model. So we routinely use GBLUP model, which has been working well. And that for the GBLUP model, all we need is the output of the single trial analysis in combination, the same G matrix. I have it from the OIT. Combination of both will get the GBV estimated for all the lines. So this tested, untested, we have GBV for all the lines. And this is the repeated analysis pipeline, goes for every single cycle, every single year. So, and we also have like a book chapter that's been currently submitted, and then which talks a lot in detail about these things, and with also some working scripts also for that with them with real data in hand. So it'll be a good resource to see how IRRI is doing that. And this is just a snapshot of the workflow, what we currently are equipped with. So I'll just go into step-by-step implementation of the genomic selection. So in the previous framework, I just told briefly like what are different steps. But right now, I'm just going into detail. Okay, in terms of training set selection, how we do that. So when we have like an OYT of 1,200 individuals and where we have marker information for all of them, we use the information effectively to pick a training set that represents the all 1,200 individuals, right? So it has to be a good representation of all the families and all the individuals. So if you see the figure on the bottom, this shows all the 1,000 individuals in the circle, red circles, and the black triangles are the training set lines that is picked to represent the all lines. So it's not like a random selection. We use an algorithm called p-means algorithm, which is developed by Akhtamir et al., which effectively picks the training set, and then that training set is used to get phenotype data from multi-environment location. So this is a cartoon information where it shows the numbers are slightly different, but the concept is the same. We have a big OYT and we pick a small training set, and that being tested. And for that, we use the same 1K RICA markers, and that's how the TS is being picked. So for example, in our program, our TS size is about 200, 300 individuals, and the entire cohort is about 1,200 individuals. So we pick a training set for every single year because we still not in a phase where we can use multi-year data, and we are transitioning to that stage in the coming years. So up until now, I pick a training set every year, use it to be tested, get the phenotypic data, predict the remaining OYT, the remaining half sets and full sets, and then get the GBVs done. So this is how the training set has been picked and evaluated. And then this is like a map representation of to show how this is being grown. So once the training set is selected, we ship them to all the TPEs, either it be Bangladesh or India or Eastern Africa, and in some cases Philippines. And then the data has been collected V4R and it's been used. So these circles here, in the past, we used as breeding zones because it was convenient because we didn't have much data on multi-location trials, so we do not know the correlation of locations. So for the convenience, we had country-based clustering, and then we did the predictions for each of the subcontinents. For example, one prediction for Bangladesh, one prediction for India, one for ESA, or sometimes two for ESA, depending on how many countries we have. But moving forwards, when we have the target product concept defined, it'll be slightly different than what was originally planned. But overall, the concept is a group of TPEs with multiple locations, data comes into the system, and the prediction is done specifically for that. So I'm not using all the data together and have one predictions and find a line that's average performing across all locations, whereas I pick a line that is performing best in a given TPE so that we get the best benefit of best performing lines in a given geographical region or for a product concept. So this is just to show the diversity of locations that we have and how we are actually set up. And each pipeline, this is a separate pipeline for Bangladesh and separate for India, separate for ESA, and the prediction is also separate. So that's what I'm trying to emphasize here. So although we have 20 or 25 locations in total, but in any given TPE, we have about 4 to 5 locations. That's what is the reality. So as I talked before, the step 3, the data collection management. So we try to use digital data collection, and then we use routinely V4R, and then the GOBI, and these two combined will become the EBS, where we have both phenotypic data sets being analyzed by V4R, and most of the genotypic data will be analyzed by GOBI and in combination. Right now, we are using V4R mainly for all the phenotypic data, and the marker data is done separately, which will eventually be integrated into an analysis system. So once this is up and running, all this will become straightforward in a push of a button. When we can collect good data, then upload the system, you can get the predictions done. You can also get the selections done very effectively, which also has an inbuilt model analysis, and everything will be there eventually. But as of now, we have semi-automated pipelines developed in-house, which we are using to do those things. And step 4 and 5, the data analytics. I'm not going to go into very detail of this, but it's just to show what are the different tools that we actively use in order to achieve these things. So we primarily use R and ASML to do all the data cleaning, data aggregation, data processing, and also for the fitting the models, we use ASML. And most of the reporting is actually done using R Markdown. There's also a tool in R where we can produce interactive reports, because in the past, we get trials from the partners, and in the end, we just share the outputs to them in the end. But there's no real way to have a two-way communication. So we thought it might be really good to have some kind of interactive report for every single trial they conduct, because there's a lot of hard work done for the season. And then we need to have a reporting structure. And then it is also really important for them to visualize the data too. Like instead of sending a very rich Excel file, it's also important to have some kind of a tool that you can start seeing and interacting. So these are HTML files that have scripts and interactive plots. So it is more like a reporting tool in addition to the summaries that we send to them during every advancement season. So these are the tools that we routinely use to do all the data analysis and also reporting in IRRI currently. So this is just a snapshot of some of the reports that we routinely share with the partners. So one is single trial reports that is showing the data quality and see, okay, how is the trial looking like? Are there any major red flags? Are we, who is connecting the trial? And how is the data distributed data statistics for them? How is the coefficient of variation, the heritability, how is the distribution of data points? So just give you a snapshot of things. And then once that is done, we do the analysis and also do the multi-location reports where we show the distribution of GB values. I'll show in a bit, and also show the correlation of traits and the trait marker frequencies in the population. So just trying to visualize things that we routinely share and give it to the partners. With that, I just wanted to also briefly touch bases and also emphasize and how we actually increase the selection intensity using GS. So there are two plots here. One on the left-hand side is a distribution of GB values for grainil on the bottom and flowering time in the top. And at the right-hand side is a distribution of BLUP values for the grainil again, and for grain in the bottom and flowering time at the top. The biggest difference between these two is, one, we have all the lines having data here, right? So if you see this figure, this distribution consists of 1,500 individuals or 1,700 individuals total. So you have value for every single one. Whereas in this plot, you will have the capacity to calculate value only for the trials that are for entries that are phenotyped in the regions directly. So instead of having 1,700, you only have 200 lines. What will happen is, if I just use the phenotypic data or phenotypic BLUP, you'll be able to only select from this distribution, and you'll be missing out so many lines that are better performing. And we just explained very clearly here. If you see the global checks distribution, they're far away from the top performing lines in here. Whereas in here, yeah, you'll be probably having those things integrated well into the system, right? So this is a clear indication that you'll be having a bigger shopping cart when you do the prediction. And that's how you're increasing selection intensity. So it's just like a description. Like most people would ask, like, okay, can I just analyze the trial and pick the best lines? You can do that. It's still possible and very valid, but you'll be missing out a lot of lines that are better, having a better breeding value. And in addition, a breeding value is important when you're talking about parental selection, because you wanted to get the benefit of the additive genetic variation. Whereas if you just use, in this case, you will not be able to do that. So I would say having the prediction values is very valuable. Is first, you can pick more lines that are better, and also you'll be able to pick better parents comparatively to just using phenotypic data in overall. So that's just to show you a snapshot of the report and also what it really means when I talk about how we increase selection intensity. Plus, these lines will also have the better potential of picking lines that have better trait marker profiles. So in addition to GBV data, we also share the trait marker profile for each of the line. So you will be able to pick lines that are having better yield protection traits like BLB or BLAST or rice tumor virus or ROMV, whatever you have in terms of these things. So I would say, like, this is the best bet for us to either advance lines or even to pick for parents in moving forward. So just sort of snapshot I wanted to show out of the reports, how we are actually effectively increasing selection intensity by using genomic prediction. So step 6, and based on the summaries and the reports, we now use the data to effectively select parents and also advance lines for the next AYT or advanced trials or stage 2 trial. And that's what happens with this, all the reports and things we generate based on the GBVs. And in terms of other works in progress, we are now moving towards a phase 2 where we now aggregated 3 or 4 years of multi-year data, and we'll be now starting to aggregate them and start predicting the progenies based on information we have in hand. And by this, we can now reduce the cycle time also, because you don't have to wait for the trials to go to the partners, get the data back, then they do the predictions, then send the advanced lines. We can now use the historical data to start predicting the progeny. So that's a stage we are currently in. And we're also trying to exploit more G/E models. We've been working closely with Eduardo and the biometrics team in IRRI to increase prediction accuracy. And we also have started deploying sparse testing strategy, where we are not trying to send the same set of experimental material to all regions, where we can distribute them and send different sets to different regions, and then we can probably compile them so that many lines having some phenotypic data is better than having only few lines tested and a lot of untested lines. So we are trying those things already in a testing stage. And then implement of selection index is also been under discussion. We have a preliminary index built, but we are trying to deploy that routinely so that we can do multi-trait selection. As Eduardo rightly mentioned, if you focus on one trait, it's easy, you can pick on that. But when it becomes 2 or 3, it becomes really complex to make effective selection. So we need to have some kind of a selection index to start picking our lines for parental selection, or even for advancement, we need to have a selection index in place. And then start integrating drone and weather data to, this is like the advantage. Once we have all the other things built, so we are also trying to involve or use the HTTP or weather data to increase the prediction accuracies too. So yeah, with that, I think the take-home message is like, there is definitely a need in rice breeding to increase the rate of genetic gain. And then GS is a very important tool to increase the rate of genetic gain, of course. And it's definitely a well-established technique to work. And as a concept, it's easy, but implementation, it requires some kind of a thought process and also a change of the holistic program, not just directly deploy GS selection, GS program, GS technique in a breeding program. And we've been doing it for the past couple of years and continue to optimize and improve it to enhance the prediction accuracies. With that, I would like to thank the entire team, the former members, all of them who has been instrumental in making this work successful so far. Yeah, thank you. I'm happy to take questions.
Thanks.